Hello, Intro Robotics. Welcome to your guide on everything analog. This should be our third lesson through the Arduino Hello World. You should be able to see this through the basic circuits. We're going to be talking about both of the last two because they're kind of closely related and you have a lot of the skills you need to deal with them already. So far we've dealt with nothing but digital reads and writes. And digital reads and writes are easy because they come in that 0 to 1 high-low method. But an analog read is something a little bit different because digital is very cute if you're able to read something that's on and off. But if you're trying to read something that has a range of data, something like the speed of an object, the temperature of something, those are the kind of things that actually need a different kind of value to deal with them. In this case, we call this analog, and it's actually going to give us a value that is a range of numbers. And I've got an example of that here. Now, this is something you should have hooked up earlier in the course. Not exactly like this, but I'll give you a walkthrough. This right here is called a potentiometer. And the term I'm going to use for them are potentiometers, trim pots, or pots. Those are all the same for all intents and purposes here. And it is actually a variable resistor. And I've actually rigged up a multimeter here, and if we walk through the circuit, we've got our Arduino connected into our power rails. Our potentiometer has its terminal 1 and 2 tied to ground and 5 volts, so it should be getting voltage through it. And its wiper, the middle lead of the potentiometer, is actually running through multimeter. It's actually going to give us a reading of what's coming out of that potentiometer, which is kind of cool. We can actually read what it is. That potentiometer is then going through an LED and back out to ground. So theoretically, as I move this potentiometer up and down, I should get an LED that dims in terms of how bright it is and because of how much resistance I give it. Let's try this out. When I turn this on, you'll notice that I can actually turn this potentiometer down counterclockwise, and I'm actually going to get numbers that are up in the 8.46 mega ohms. That's millions of ohms, 10 to the 6. And obviously the LED is off at this point. That much ohmage, we are getting a much smaller amount of amperage. And this is again tied to that Ohm's law piece. The smaller the resistance, if we get down into kilo ohms, we're going to eventually, at this point we probably still don't see an LED turning on. We probably don't see an LED realistically until we get down into the about 1000 ohm. I know TinkerCAD starts to show it, but in real life, we're probably not getting a lit LED until this area here, if we're being realistic. You can get trim pots in all different sizes. Ones that range from 0 to 10,000, 0 to 1,000 are fairly common. Obviously, this one we're looking at, it goes from 0 to millions. Probably 10 or 100 million. That's okay. You'll notice that when I get down into the 1.67 ohm, your LED actually explodes, and if we float over top of it, it actually tells you the calculation that it's getting way too many milliamps to actually function. Now, we can use this because in addition to showing how much ohmage goes on this trim pot, it also splits voltage. And I'm just going to show you a version of this. We can actually see that we're getting a lot of voltage. And the fact that we get a negative number is not that important here. It just means that I've got my leads backwards, and that's not the end of the world. On this one, it's going to give us different voltage values, and we can use that to actually be read by our Arduino, which is the first part of what we're going to talk about, which is your analog read. So let's try reading what's happening on this trim pot. We're going to go stop our simulation. We're going to change our circuit just a little bit. I'm actually just going to delete this wire here, and I'm actually going to run a wire from the center of the trim pot over to A3. Again, I'm going to put nice square edges on my wires so we can see where they're all going. Life is good. We're then going to go over to our analog read. You can read the guide here as to what it's doing, but this is very similar to a digital read. It's going to be simply reading what's coming in off of the Arduino. I'm going to go to the code. I'm going to replace the code I have. I'm going to walk my way through it. I'm going to zoom in on this so we can read it properly, as we usually do. Alright, so it starts off with, on line 1 here, a variable, an integer variable, just like we're used to, called analog pin, and it's equal to A3. I've already hooked up A3, so life is good. I don't have to change this. If I'd hooked up A1, the easiest way to fix it would be to actually just change this number here to A1 or A0 or wherever I'd hooked up my trim pot. And you can see the comments say, potentiometer wiper, middle terminal, connected to A3 and outside leads to ground and 5 volts. Now notice that you have normal pins, these ones, and when you float over them in TinkerCAD, they have the letter D in front of them. That means that these pins are queued for digital communications, meaning ons and offs, whereas the A pins, at the bottom of your Arduino board here, are actually queued for analog communication. So whenever possible when doing analog, we're probably going to be working with analog with the A pins. There's a couple noteworthy exceptions to that, but we'll get to them eventually. We then create another variable called VAL, where I'm going to refer to this as value. Before I rearrange it, I'm going to refer to this as value throughout this code, just to keep it simple, and we start it equaling to 0. Let's go to our setup. Setup's easy. Serial begin 9600. You've seen this before. We're going to talk through our serial monitor. Value equals analog read of the analog pin, which is A3. Now, just like a digital read, we're just going to read whatever's happening on that analog pin, and we're going to get a number back here, which is easy to do. Okay, we're then going to serial print that value down into our serial monitor. Let's try out this code. Once we hit play, we get the number 164. I'm going to zoom out a little bit on here so I can play with the trim pot, and we can play around with it and see what we get. As I scroll down, you'll notice that I get numbers that are closer to 0. As I scroll up, we're going to get numbers that should, theoretically, max out at 1023. Wow, that's fancy. It's almost like I knew it was going to happen there. The trim pots are actually giving you a value in, the reason for the 1023 is that there's 1024 possible numbers. We actually have a binary number here at its core, and that's why we have this number. So we're going to get a number between 0 and 1023, but that's kind of cool because it means that I can have a dial that's going to give me actual computer information. What can we do with that? Well, we could do all sorts of things with that. In this case, we're going to do something very simple. We're just going to light up an LED with that particular number and actually make it happen. Actually, before that, yeah, we're going to make the LED work. All right, so let's talk about analog writes. So closing this down, let's make an LED that dims. Now, basically, when we hook up an LED to a digital pin, it turns on or it turns off. We're going to hook up a new circuit over here. I'm just going to make this a nice yellow LED. Going to put a nice 470 ohm resistor on it. Okay. I'm actually going to hook up my power rails across the board. This is something you can do if you want to use both sides of your breadboard. Highly recommend it. You can just jump your breadboard across the other side, and now these power rails are in essence connected to the other power rails. Life is good. So I'm going to grab some code here, and I'm going to take a look at what I'm going to be hooking up for this analog write. And I'm going to go over to my analog write command in Arduino. Okay. And this is going to be using something slightly different. Now, when we talk about the analog read, those analog pins actually read a variable voltage. They're reading what the voltage is between 0 and 5, typically. Analog write uses something a little bit different. It's something called PWM, or pulse width modulation. And pulse width modulation, I'm just going to grab the code here very quickly. I'm going to click on the PWM description here, and it'll come with a really interesting diagram. Now, pulse width modulation is the idea that could you communicate analog data with a digital pin? You'll notice that all of the graphics here use what's called a square wave, which means that all of the lines are either 0 or 5 volts. And the answer to the question is yes, you absolutely can communicate partial information using digital signals. You use it by modulating the amount of time between the signals. In this case, we've created what's called a duty cycle. All right, duty cycle is a standardized amount of time that the Arduino is expecting between signals. And it asks how long has the pin been on during one of these duty cycles. So for the example here, this is a 0% duty cycle at the top where we have 0 volts the whole time. Likewise, 100% duty cycles, 5 volts the whole time. But the internal ones, these ones in the middle, are the really interesting ones. What if we left the pin on for exactly half of that duty cycle? Okay, in this case, we would give an analog write value of 127. You'll notice that the analog write comes between 0 and 255. That's important. Analog read is between 0 and 1023. Analog write is going to be between 0 and 255. We're going to deal with that in a minute. That being said, 25% duty cycle means we're on for 25% of the time, off for the rest of it. Okay, on 25, off for 75. That's going to give us 25% of the time on. Likewise, 75% is the exact opposite. On for 75, off for 25. This allows us to communicate analog information across a digital pin, which is super, super awesome. It works for us here. So let's go back to our TinkerCAD. Let's go to our code. And I'm very simply going to take this code that I created, and I'm going to use a trick. I'm going to put a */ on one side. I'm going to put a /* on the other. And you'll notice that all of my code just turned orange. That's on purpose. That's actually going to allow me to simply add some new code and run with it for now, so we can talk about some other stuff. All right? Now, what I'm going to do here is we're going to read through this code as to what we're going to do for this analog write. It says integer variable LED pin equals 9. So that tells me that this LED that I just hooked up here, I probably have to hook it up to pin number 9. We're going to make the code go away for a second and do just that. We're going to go to negative here, and then we're going to go to pin number 9 here. Again, I'm a big fan of making sure your wires are well organized. It makes life better for everyone involved. There we go. Awesome. Okay, now we know that we've got an LED on pin number 9. We go back to our code. Okay, we have an analog pin, potentiometer connected to analog pin number 3. Okay, I'm going to change this to A3 because I believe that's a slight error there, but we'll sort that out as we go along. Value is again equal to 0. This is a lot of the same code we've already dealt with. In this case, we have void setup. In this case, we're going to go pin mode. LED pin is an output. And that kind of makes sense. Basically, this is going to allow us to use that LED pin just like we did with previous designs. Okay, void loop. Okay, value equals analog read of analog pin. Hey, that's exactly the same as what we just dealt with. That's awesome. We're then going to analog write the LED pin value divided by 4. Now let's break down how this works. We got a value in on the analog pin that is going to come in between 0 and 1023. We've already tested that. 255, in this case it's actually 256, is 1/4 of that. And so we're actually going to take whatever our value is, a number from 0 to 1023, 1024 possible outcomes, and we're going to divide it by 4 to get the same number as a percentage against 0 to 255. That's what our pin is actually expecting. And so that's going to allow us to actually build this as an output. LED pin, we know this is going to be pin 9. Value divided by 4 is going to be the number it assigns to it. This is controlling an LED using digital signal instead of using something electronic like a potentiometer. Let me just slide my window over here, perhaps zoom out a hair. Let's take a look at our circuit and let's run this thing. Start code. From here, you're going to see that as I rotate this trim pot, that yellow LED is going to actually brighten up, or it's going to be not as bright. Now, let's just read into what's going on here. Let's add some pieces to this that we know how to use. I'm going to add a serial dot begin in our setup, 9600, just like we normally do. And then in our loop, before we analog write this, I'm going to go ahead and I'm going to do a couple things. I'm going to do a serial dot print new line. New line. Okay, and I'm going to say pin value. Now, I actually want to display the words pin value in my serial monitor, so I'm going to actually put them in quotation marks, just like so. Everyone can see that. Oop, that was the wrong one. Pin value equals. Okay, from here, I'm going to actually put a new serial print, and I'm not going to put a new line, and I'm just going to print VAL. Okay? And this is going to allow me to actually see the pin value. I'm going to print a couple more things here. I'm actually going to print the output value as well. So I'm going to copy this and paste. I'm going to put the output value. And of course, the output value is actually this value divided by 4. You can see that below here. That's what we're actually going to see. So let's do this. Let's actually run this code. Let's see what happens. I may have put my new line in the wrong spot. I did put my new line in the wrong spot. So let's see what happened here. Okay. I got pin value. I need to put my new line at the end of this, I believe. Let's try this out. Pin value. Okay. And I just need to stop this briefly and put a couple spaces here so we can visually see stuff. There we go. Okay. Oh, I see what I did. I put one too many new lines. Apologize. That's what I'm looking for right there. Okay, so right now we're seeing a pin value of 20 and an output value of 5. That makes sense because the output value is always going to be 1/4 of what the pin value is. So let's zoom back in on our circuit here and let's actually find out what we're doing. So if my pin value, as I turn this, goes up, you'll notice that my pin value increases, my output value decreases, and the light turns on. This number, the output value, is the value the light is actually getting assigned as a percentage of voltage between 0 and 255. If we keep turning this, we can see that output value go up, and at its very max, our pin value maxes out at 1023. Our output value maxes out at 255, and at the end of the day, we've now done an analog read and an analog write. I hope you took something from this. Hope you learned a few things. Good luck with the assignments, and we'll see you in office hours if you're having trouble with it.